Here's something that stops me cold every time I think about it. In November 2024, 4 astronauts flew around the far side of the moon. Not just past it, around it. They lost all contact with Earth for 30 minutes. No signal, no GPS, no communication of any kind. Just 4 humans in a capsule, further from Earth than any human being has ever been in history, in complete radio silence on the other side of the moon. And while they were there, they took pictures. Not the grainy gray snapshots of Apollo. High-resolution digital images captured with modern optics in lighting conditions that have never existed in any photograph taken by a human being before. Pictures that show physics that textbooks describe but cameras have never actually caught. When those images came back, scientists did not say nice photos. They said, wait, look at that. Look at what that actually shows. So that's what we're going to do today. Look at what the images actually show and understand why each one of them is more interesting than it looks at first glance. Quick background, because it matters for what comes next. The Artemis II mission was NASA's first crewed test flight of the Orion spacecraft and the Space Launch System, the most powerful rocket ever flown. The crew, Reed Wiseman, Victor Glover, Christina Koch, and Canadian astronaut Jeremy Henson. Their trajectory was a free return loop around the moon, meaning the spacecraft swung around the lunar far side using the moon's gravity and came back to Earth without needing to enter orbit or land. It's a figure-8 path, and it's the same basic approach Apollo 8 used in 1968. But the hardware is different. The crew size is different. The cameras are different. And crucially, the mission timing is different. Artemis II flew a specific trajectory that put the crew in positions relative to the Sun, Earth, and Moon that created photographic opportunities that simply did not exist during Apollo. That's not hype. That's geometry. And geometry, when you're 400,000 kilometers from home, produces images that are genuinely unlike anything captured before. Let's go through them. The first image that stopped people was taken early in the mission, before the crew even reached the moon. It shows Earth at night, not the classic blue marble shot, but the dark side. City lights scattered across the continents, and the entire disk of the Earth is faintly, softly illuminated by a gentle gray-blue glow. That glow is moonshine. Literal moonshine, sunlight reflecting off the moon, bouncing back to Earth, and then reflecting again off Earth toward the camera. Now you might think, of course, the moon lights up the Earth at night. We can see that from our backyard. But here's what's different. From the ground, you're looking at the moon. You're not looking at the Earth from space in full darkness, while the moon is off to one side, washing the entire planet in reflected light. The geometry of that image, the angle, the distance, the darkness of the surrounding space, makes the Earth shine visible in a way it has never been photographed before. And there's something else in that image. At the edge of Earth's atmosphere, running along the limb of the planet, there's a faint orange-yellow band. That is the sodium layer, a thin shell of sodium atoms sitting about 90 kilometers up in the mesosphere, created by the constant rain of micrometeoroids burning up as they hit Earth's atmosphere. Every day, tiny particles from space vaporize and leave sodium behind. From the ground, you can detect it with lasers. From 400,000 kilometers away, in the right lighting conditions, you can actually see it glowing against the dark of space. That band in the photo is not processing. It is not an artifact. It is a real atmospheric feature that has been documented scientifically, but has rarely been so clearly visible in a crude mission photograph. When Artemis II swung around the moon, the crew photographed the far side, and the contrast with the near side is immediately visually striking. The near side of the moon, the face you see every night, is roughly 30% covered in dark, smooth plains called Maria, from the Latin for seas, named by early astronomers who thought they were actual bodies of water. They're not. They're ancient basaltic lava flows formed billions of years ago when the moon's interior was still hot enough to flood large basins with magma. The far side has almost none of this. It is almost entirely pale, heavily cratered, highland terrain. When you look at both hemispheres side by side, they look like two different worlds. Why? Scientists believe this asymmetry comes down to the thickness of the crust. The far side's crust is significantly thicker, potentially by 10 to 20 kilometers in some regions. When large impacts hit the near side billions of years ago, the thinner crust allowed magma to well up and fill the basins. On the far side, the thicker crust contained the impact damage without allowing that flooding. But why is the crust thicker on the far side in the first place? That's still an open question. Current leading hypotheses involve either the thermal history of the early moon, with the near side staying warmer longer because it faced a still glowing young Earth, or the possibility that two smaller moons merged early in lunar history. Neither is confirmed. The asymmetry is real. The explanation is still being worked out. What the Artemis II images captured is that contrast in high resolution from a human-crewed spacecraft for the first time. The geological difference is not subtle. It is enormous. One of the specific geological features captured during the far side pass was the Orientale Basin, one of the most visually striking impact structures in the entire solar system. Orientale sits on the western limb of the moon, and from the right angle it looks almost like a target, a bullseye of concentric rings spreading outward from a central depression. The outermost ring is over 900 kilometers across. Those rings are not coincidental. They are the frozen record of what happens when something very large, probably an asteroid tens of kilometers wide, hits a planetary body at high velocity. The impact releases energy comparable to billions of nuclear weapons in a fraction of a second. The crust behaves, briefly, like a fluid. It rebounds. It collapses. And as it settles, it locks into these concentric ring structures, like the rings that form when you drop a stone into thick mud, except the mud is rock, and it solidifies in place over millions of years. Orientale is particularly valuable to scientists because it is one of the best preserved multi-ring impact basins in the solar system. Most large impact basins on the moon have been degraded by subsequent craters, lava flooding, or billions of years of smaller impacts. Orientale is relatively intact. Studying it helps planetary scientists understand impact physics that applies not just to the moon, but to every rocky body. Mercury, Mars, the moons of the outer planets. Seeing it from a crude spacecraft at an angle that orbital photography rarely achieves adds a layer of perspective that data alone doesn't provide. Here's something small, but genuinely cool, that showed up in the Artemis II images. Several photographs contained isolated single pixels that appear as bright white dots, not lens flare, not dust on the sensor. They are cosmic ray hits. In deep space, away from Earth's magnetic field and most of the protection our atmosphere provides, the radiation environment is significantly more intense. High-energy particles, protons, and heavier atomic nuclei, accelerated by supernovae and other extreme events across the galaxy, pass through the spacecraft constantly. When one of those particles hits the image sensor at the right angle and energy level, it deposits a small flash of charge in a single pixel. The camera records it as a white dot. Every one of those dots in the Artemis II images is a particle that traveled, in some cases, from outside our solar system, crossed billions of kilometers of space, and hit a sensor a few centimeters wide inside a spacecraft orbiting the moon. It's a minor image artifact and also a direct record of the cosmic radiation environment that astronauts on deep space missions have to live inside for future missions to the moon's surface and eventually Mars. Managing that radiation exposure is one of the central engineering and medical challenges. Those pixels are a small visual reminder of it. This is the image sequence that generated the most genuine scientific excitement. At a specific point in the trajectory, as Artemis II swung around the far side, the sun moved behind the moon from the crew's perspective. The spacecraft entered the moon's shadow, and for 54 minutes, the crew had a front-row seat to a total solar eclipse, unlike any ever photographed by human eyes. From Earth, a total solar eclipse is spectacular but brief, usually under 7 minutes, and only visible from a narrow strip of the planet's surface. From the Artemis II position, the geometry extended the eclipse to 54 minutes. The moon was effectively blocking the sun for nearly an hour. The images from this period are remarkable for several reasons. First, the corona. The sun's outer atmosphere, the corona, is only visible from Earth during total eclipses because the photosphere is too bright. But from where Artemis II was positioned, the corona was visible as a structured, dynamic halo of plasma extending outward from behind the moon. The corona is hotter than the sun's surface, reaching temperatures of over 1,000,000 degrees. And the reason for this is still an active area of solar physics research. These images add to the corpus of high-resolution corona photography from a unique vantage point. Second, Earthshine on the moon. During the eclipse, the crew could see the lunar surface, lit not by the sun, but by reflected light from Earth, Earthshine. The moon's surface, in deep shadow, still had a faint visible illumination because Earth was reflecting sunlight onto it. In the same frame, the sun's corona in the background and Earthshine on the moon's surface in the foreground. That combination, both phenomena simultaneously visible in a single photographic sequence, has no prior equivalent in the record of human space flight. Third, the ecliptic plane. With the sun blocked and the surrounding sky darker than any environment on Earth allows, several planets became simultaneously visible. They appeared in a line, not randomly scattered across the frame. That line is the ecliptic plane, the flat disk of the solar system. The planets orbit the sun in roughly the same plane that the Earth does, so from any point in the inner solar system, they appear roughly aligned across the sky. In those eclipse images, you can see that alignment visually. It is the geometry of the solar system made visible in a single photograph. The final sequence worth understanding is the Earth set. the images taken as Earth appeared to set behind the lunar limb from the crew's perspective. From Earth, the moon appears to rise and set because Earth is rotating. But from a spacecraft near the moon, the geometry is different. The spacecraft itself is moving, and as it swings around the lunar limb, Earth passes behind the moon's edge from the crew's point of view. The moon doesn't rotate significantly relative to Earth because of tidal locking. The same gravitational interaction that causes ocean tides on Earth has, over billions of years, slowed the moon's rotation until it matches its orbital period exactly, which is why the same face always points toward us. It also means that from the lunar surface, Earth barely moves in the sky. It just hangs there, which makes an Earth set, as seen from a spacecraft moving around the moon, a function of the spacecraft's motion rather than any rotation. The Earth-set images also demonstrate telephoto compression. Because the cameras were using longer focal length settings, the moon's surface in the foreground and Earth in the distance appear much closer together in apparent scale than they physically are. Earth is nearly 400,000 kilometers away. The lunar surface in the foreground might be a few kilometers below. Telephoto optics compress that distance, making Earth look almost touchable above the horizon. It's not a distortion in a misleading sense. It's physics. But understanding it makes you appreciate the image more, not less. Artemis II was a test flight. No one landed. Nothing was deployed. The primary objective was to verify that the Orion spacecraft and its life support systems work correctly with humans inside on a deep space trajectory. It did that. But the images it returned did something else. They documented in human eye photography, physics, and phenomena that we knew about analytically but had never seen from this vantage point, in this light, at this distance, through human eyes. Artemis III will attempt to land astronauts near the lunar South Pole, a region of permanent shadow in some craters where water ice almost certainly exists. Artemis IV will bring crew to the Gateway, a small space station in lunar orbit that will serve as a staging point for increasingly ambitious surface missions. The moon is not just a destination, it is a proving ground. The life support systems, the radiation management, the navigation, the surface operations, everything learned there feeds directly into what a crewed Mars mission will require. But if Artemis II showed us anything, it is that even a test flight, even a trajectory designed primarily to check hardware, produces images that make you stop and look twice. Because when you get far enough from Earth, the universe starts showing you things you hadn't quite seen before, even if you thought you already understood them.